talk. Honda-san, please.
Yeah. So thank you for introduction. So I'm Masazumi Honda. And my background is high energy physics, and so I'm usually working on various topics simultaneously. And today I want to introduce idea of one of my topics called resurgence. And so that's why the resurgence is in the title. So roughly speaking, this is a way of one of the ways to make sense non-convergent. Okay, so let me start with the introduction. So we are basically theorists. So in theoretical science, so we often encounter the following situation. So we quite often, so we want to compute something, some quantity. So let us say f as a function of some parameter. And so f and g are depend on your problem. And for example, f could be an observable of quantum field theory, f could be a solution of differential equation, so whatever. So some quantity and parameter. Yeah, but for interesting problem, quite often we cannot compute it exactly in many situations. So, but cannot compute. So quite often we cannot compute it exactly, despite we want to know what behavior of it. Yeah. And for that case, so what should we do? So to me, there are three choices. So one is to ask experimenters to one is to ask people to measure to do experiment and measure that quantity. But I cannot do that. And another choice is to do some numerical simulation to directly compute this. And so another approach is, of course, with some approximation. And so here, let us consider this possibility. And so when we want to compute quantity exactly, so one will be just approximation. Approximation is perturbation theory. Perturbation theory. So idea is to expand quantity around some simple case. For example, when G is a coupling constant or strength of interaction, so quite often we start with non-interacting case and we expand it around the free theory. So schematically, we typically have this kind of series. And so we can take G0 equals 0 without generality by defining the parameter. And so here, question of my talk is so is it good approximation in general? Or another question is So given the coefficient of the perturbation theory, is there a way to get the exact result by determining the perturbation? Okay. So do you have a question so far? Okay, it's quite abstract, and so let me discuss using some explicit example. So let us start with a very, very simple example. So yeah, suppose the situation that so we compute perturbation of some quantity, and then we get this kind of perturbative space, and so this can be written in this way, and so you still have to compute this, but we have to be careful about the region of G. So when the absolute value of G is less than 1, so this is convergent, so we can compute it like this. And so for else, so for other case, so just naive sum is divergent. But there is a way to make sense this quantity, this quantity to the outside of that region. So by using simple analytic definition, so one may estimate P for any G, but okay, and so but in general this is not true. But when we don't, so in general, the perturbation theory may have something which cannot be written in terms of power of G. So if we don't have something cannot, that can't be written by power of G. It is supposed to be. It is supposed to. It is expected to be true. And so this kind of thing is at least in physics called non-perturbative effects. Okay. And in physics, the form is typically like something like exponential of 1 over G. And so for this case, the series is convergent. And so if we get the convergent series in physics, in the actual problem, so we are basically lucky. And so we can estimate, we can estimate exact result. And so next, so I will turn to one non-trivial example. So you have a question about the first example. Okay, then next I'd like to consider one non-trivial example. And so for simplicity, I first give an exact answer. And where gamma is a function called the incomplete gamma function. And so the integral representation is given by this. Okay. And so if we consider perturbative small g expansion of this guy, we get the following series. So we get this kind of series. So can you perform some of this series? So it turns out it is known that this series, just neither sum of this series is an infinite answer unless g is 0. For g equals 0, it's 0. So this is non-convergent series. So in other words, the radius of convergence of this series is 0. So what should we do in this situation? And standard way to rescue this kind of situation is Borel resummation method called Borel resummation.
Question.
Yes.
In the beginning, you said we are gonna expand the function, the series, and expansion point might be important.
Very important, must be important.
Yeah, in this case, you chose g equal to 0 as an expansion point, but
Yes.
point,
Hmm?
is it good point in the sense that in the first line definition, it involves exponential 1 over g, and from beginning it's like divergent.
No, it's not divergent. Divergent cancellation. Yeah. So in general, if we change it, points to be expanded, so property of series become quite different. So sometimes it's convergence, sometimes it's not. For example, for the lattice case series, so it is known that so sometimes the big coupling expansion is not convergent, but usually strong coupling expansion is convergent. So this is just the example. So without specifying parameter and point of it to be expanded, so we cannot ask this question. So here just we are focusing on small g expansion. So suppose we try to expand the function f by the following formal series. Given by this coefficient. Then in Borel summation, first we introduce an object called Borel transformation, which is given by series. So this is called Borel transformation. And you see that there is basically a factorial factor in denominator. So this makes convergence better. So in general, so even if the original part of a chip sheet is not convergent, this one could give convergence series. Then for every summation, is defined in the following way. Now, precisely, I'll write down a definition for a summation along direction theta. This is given by basically a Laplace transformation of Borel transformation.
So you can ask,
Yes.
what is A?
A is some constant.
Integer.
It does not have to be integer, but typically it's integer in physics program. It's it could be complex, I guess. Yeah. But this cannot be a negative integer. Yeah. So A is basically arbitrary. Yeah. So it depends on your problem. So it's fixed by the leading order of pattern. So typically A is 0. Yeah. So typical physics problem. But sometimes we start with problem. Yeah. And quite often theta is basically 0. But when G is a real parameter. Okay, this is the formula. And why is this formula good? So first, so we can show that this formula gives the same. Okay, if we consider small g expansion of this object, the small g expansion is the same as the original shield. So we can check by using the integral representation of gamma function, and then we have a cancellation of this guy from the Laplace transformation. And another good point is that depending on the property of this integral, so this object may have a finite answer for any g. So it seems it's better than original perturbative shield, which just give an infinite answer. Yeah, for non-zero g. Yes.
Yeah, I don't get this push over bound of this integral. Is it like infinity in the direction of theta, the complex plane?
Yes. Something like that. Yes. Something like that. But in most of physics problem, we take it. Yes. Okay. So now I want to let us apply this method to this series. So the Borel transformation is given by this, because there's a simple cancellation factorial by the gamma function here. And so we can get so we can perform this sum. It's simply by 1 plus t after analytic continuation. Then we consider we compute the Borel summation along the real positive axis. We have this integral, and after rescaling t by gu, we get this integral representation. So this is exactly the same as the original function. So this looks nice. And so now I think I think you're wondering when this kind of scheme works. So next, yeah, finally, yeah, okay, I will finish by mentioning what's the problem of this approach. So, yeah. So indeed, Borel summation is not magic. And there are couple situations. So this is a complex plane of T called Borel plane. And suppose we want it, so typically in typical physics problem, so we usually take this direction for the quantum. And so in general, so the Borel transformation has a singularities in the complex plane. And sometimes this is false, sometimes it is branched up. And also, sometimes or usually in physics problem, Borel transformation has a singularity along the integral quantum where we want to perform the Laplace transformation. And for that case, the integral becomes ill-defined. And we may want to deform the integral quantum to avoid the singularities. So by this scheme, so we can get a finite answer, but we encounter another problem. So if we avoid the singularities in this situation, the value of integral depends on how to avoid the singularities. Yeah. So for that case, the Borel summation has an ambiguity. And so we don't want the unambiguous answer for example, for the answer of physics. So this is a problem. And so when the singularity type of singularity is false, this ambiguity can be typically estimated by picking up residue. Then we get something like exponential minus 1/g. So this means that the ambiguity here is a non-perturbative effect. This is interesting. So far we have only considered perturbative sheaves, but perturbative sheaves seems to know something about non-perturbative effect. And finally, I will finish in a minute by introducing the idea of resurgence. So resurgence is a method which is expected to rescue this kind of situation. And so I will skip similar things, but So if you are interested in, so I can answer. Yeah, if you ask question, if you ask me questions, I can answer in detail. So and what is the idea? I just show idea. So we had a ambiguity in model resummation. So we had ambiguity, and the idea of resurgence is that if we carefully compute the non-perturbative effects, for example, by using saddle point or some, in another method, if we carefully compute the non-perturbative effects, so in various problems, it is known that this one, non-perturbative effect also has some ambiguity, and the amount of the ambiguity is the same as for the summation in various situations, and at the time is minus of for the summation. Then the one with the summation, then so we get the kind of cancellation of ambiguity for the whole answer. So each part has ambiguity, but that ambiguity is cancelled when we take the both contributions. And it seems that in various examples, at least in quantum field theory, this method, this scheme may work. And so, but since perturbative expansion is ubiquitous in many areas, so I'm curious about whether this kind of scheme works in other areas. So this is the end of.
Okay, thank you very much, Honda-san, for very pedagogical, clear explanation of this intricate subject. So, any question?
Yes.
So in this situation, you would get this convergent theory.
Yeah.
And then you say, oh, I have a recipe to turn it into a final result.
Yes.
So let's imagine it's a simple case where there's no similarity on the real axis. You can do the thing and you get the Borel resummation and it's a finite result.
Yes.
Is it a physical result? You can imagine that you have other recipes that Borel resummation to also extract the finite result from this non-convergent theory. Why would the Borel resummation give you the right physical result? Is there a case?
Okay, but
resummation, check the physics, and it's correct.
Okay, great. Okay, so maybe I have two answers. So one is mathematical answer. So this way is not okay. This is not okay. This is not the only way to resolve perturbation. For example, so we could replace this function. For example, there are also other more general scheme. For example, something like that. So it is not the only way. So it is But when this kind of scheme works, so I expect that other scheme also give the same answer. And also and I have another answer in the context of physics. Just by looking at perturbative shield, so it's hard to see where the answer is true, but in many situations, so we can explicitly check whether the answer is true or not. For example, if F was a solution of differential equation, so we can easily check my guess on the answer is correct or not. But if F was given by huge dimensional integral, so it may be difficult, but we can do some consistency check. Yeah. For example, by looking at the existence of a non-trivial saddle point, so we can check whether there should be some other kind of non-perturbative effects or not. Yeah, but in general, so it's hard to, hard to check whether for summation is exactly yeah, it's still developing. Yeah.
So there's some examples of these divergent series where a lower order perturbation is still active, right?
Yeah, when G is small, basically.
So, yeah, but it's still divergence.
It's still,
Is it related to this cascade of how perturbative effects do you think? Is that where that's coming from?
yeah. So, okay, good question. So there is also a way to estimate accuracy of approximation by truncation. And it is also known that the error behaves like this. Yeah, for large order expansion. If we want, I can explain. I can elaborate. Yeah. Yes. In QED. Oh, QED. Yeah, good question. So first of all, I'm not sure if there is this QED in non-perturbative sense. Yeah, I'm not sure. So yeah, this is just by looking at kind of. I think there is a well-known saddle point, non-trivial saddle point in QED. But we also know that we also expect that the perturbative shield in QED non-convergent, and so there should be singularities. Yeah, but I'm not sure if there is a singularities on right plane. Yeah. So in this sense, so several people are working very hard to compute the perturbative coefficient of QED. So I'm curious about the summation property in QED. So I don't have a clear answer.
Okay, any other questions? Zoom audience? Okay, if not, maybe people at the common room can discuss further firsthand. Okay, let's thank the Honda-san again for his very great talk. Thank you very much.